Okay, so it seems like we are live on air. I apologize for not being live on air for the first part. We were fighting a battle like Don Quixote against the windmills in La Mancha and lost, like Don Quixote. In this case, instead of the windmills, he was Googling out. That happens to work essentially always, apart from today. Anyway, as I said in my email accompanying the link to the second part of the lecture, I will post a recording from last year. So you haven't missed anything. Of course, no, you missed a great first half of the lecture where your colleagues in the lecture room were on fire. I have to tell you that. They were absolutely fantastic, doing all kinds of exercises on linear transformations. And just to make you feel that you didn't lose anything, even though you did miss some great stuff going on in the lecture room, let's start the second half by warming up with yet another exercise having to do with linear functions. So suppose somebody goes to Sherlock Holmes and says, "Dear Sherlock, here's a linear map from R2 to R2, and I tell you that T of 20 is 42, and T of 11 is 02. Sherlock, I want you to find out what is T of 0 pi. What is Sherlock's answer going to be? That's supposed to be 4 and 2, yes. That's a 4. It came out a bit slim. The question was, is this supposed to be a 4? Yes, it's a 4. Perhaps it's better if I just rewrite it. Anyway, it doesn't really matter what that is. Huh? I'm just screwing up my beautiful vector there. There you are. Sorry, excuse me. I should never say that on YouTube. So what is Sherlock Holmes going to do? Well, the first thing he's going to say is exactly the same thing you're going to say right now, namely elementary, Dr. Watson. I can solve that in my sleep. I hope you don't, because otherwise you don't sleep, but that's another matter. So how would Sherlock Holmes go about solving this murder mystery? He would just analyze the data that he has at his disposal. That's exactly like machine learning guys like you do, isn't it? You're computer scientists, apart from being detectives, so you just analyze the data that you have at your disposal. And you figure out what these data actually tell you. And it tells you a lot. So for instance, if you know that T of 02 is equal 42, this will tell you what T of 10 is. What is T of 10? Okay, so let me sort of help you a little bit. I know you don't need it, neither you at home nor the people here in the lecture room, but let's do it. Can you actually write the vector 20 in a simpler form that has something to do with 10? Yes, for instance? When you say yes, you should then provide an answer. It's 2 times 10, isn't it? No. Isn't it? Well, because 2 is 2 times 1, 0 is 2 times 0. So 20 is actually 2 times the vector 10. You just multiply by 2 every component in the vector 10, and you get 20. So far, so good. But hey, Sherlock, you are Sherlock now. I'm just Dr. Watson. I tell you, Sherlock, wasn't it the case that T were linear? And you as Sherlock would say, yes. So what is this thing equal to? It's 2 times T of 10, as your colleagues are saying. I'm sorry, I'm running out of space here. But you can see there is a missing brace, which is not missing, it's just you cannot see it. Okay, but T of 2, 0, you know it's 4, 2. And that's 2 times T of 1, 0. So what is 1, 0? It's 2, 1. You just take 4, you divide it by 2. You take 2, you divide it by 2, and you get 2, 1. So elementary, Dr. Watson. If T of 2, 0 is 4, 2, T of 1, 0 is 2, 1, because T is linear. But now, you know, I can hear your colleagues at home who can finally watch us. They're saying, yeah, well, why does it help us to figure out what T of 0 pi is? You know, your colleagues in the audience are saying, wait a minute, I've only examined only part of my evidence. Dr. Watson, I also know something else about T. And since this is a murder mystery, let's make this red, the blood evidence. The blood evidence tells us that T of 1, 1 is 0, 2. So can our Sherlocks here use this information to figure out what T of 0, 1 is? Let's see. 0, 2 is equal to T of 1, 1. And now I know what T of 1, 0 is, and I would like to use this piece of evidence. So can I actually write 1, 1 in a way that uses 1, 0 and 0, 1? Well, we did it before, isn't it? 1, 1 is nothing but 1, 0 plus 0, 1. So let's do that. And let's give ourselves a little bit more space to work with. And I reveal it one bit at a time. Now, if you were Sherlock Holmes, what would you do? You know that T is linear, so what is this thing equal to? Absolutely, you use recursion somehow, one of the properties of linearity. So that's T of 1, 0 plus T of 0, 1, which is the thing that I want to figure out. And I can figure it out now. Why? Because I know what T of 1, 0 is. It's written over here. It's 2, 1. So, ladies and gentlemen, what is T of 0, 1? Okay, let's summarize what we figured out so far. Now, forget about division. Think subtraction. If these were numbers instead of vectors, how would you solve this equation to figure out what T of 0, 1 is? You would just subtract, you would just move this thing here to the other side. As the Doors would have put it, but you're far too young for that, break on through to the other side. So we just move this thing on the other side. But to do that, we just turn this into a minus of that vector. So this is actually telling us that T of 0, 1 is equal to 0, 2 minus the vector 2, 1, which is minus 2, 1. You know, vectors are like numbers. You can subtract them from one another. Okay, but now it's easy. Because what is it that Dr. Sherlock Holmes was asked to figure out? We asked Sherlock Holmes, what is T of 0 pi? Well, you know that T of 0, 1 is minus 2, 1. So what is T of 0 pi? It's minus 2 pi and then pi below. Because it's just pi times what T does to 0, 1. You know, this may sound mysterious. In fact, it was, that's why I turned it into a murder mystery with Sherlock Holmes and Dr. Watson. But in fact, Sherlock is absolutely right. That's elementary. Once you figure out where the trick is. And the trick is that there is no trick. You just need to use the power of linearity a few times and everything falls through. I encourage you to try this at home, and you will see that it's piece of cake once you know what T being linear gives you. And it's a lot. In the previous part of the lecture, one of your colleagues asked me, but why do we gain from linearity? Well, I mean, I hope that these examples are giving you an idea of what we gain. A lot of nice properties. In fact, what we are going to see now is probably the nicest property of them all of linear functions. We will see the linear functions are exactly the functions that are induced by matrices. So being a linear transformation and being a matrix transformation are exactly the same thing. If somebody gives you a linear function, you can always find the matrix that induces that function by matrix multiplication. Moreover, if somebody gives you a matrix transformation, you're guaranteed that that transformation is a linear function. So let's do the easier part first. And the easier part is, let's show that every matrix transformation is linear. Are we all on the same page? Is it clear what we are trying to do? I hope the silence means yes. Otherwise, scream now, metaphorically speaking. Or you can also do it physically if it sort of helps release the tension. Sometimes it helps me. It doesn't help all of the other people around me, but that's another matter. Okay, so suppose somebody gives us a linear transformation, a matrix transformation from Rn to Rm. T is a matrix transformation, means that T of x is of the form, is always A times x for some fixed matrix A. Now, what are the dimensions of this matrix, by the way? So how many rows will it have and how many columns? So it goes from Rn to Rm. So this means that this vector here is an n vector, n-dimensional vector. So the number of columns of the matrix will have to be, this should be multiplied by A, so the number of columns will have to be n as well. So the number of rows will be m. So that's the dimension of the matrix. It goes the other way around. So this goes from Rn to Rm. So this means that the matrix will have to be m times n. Oh, the first one is Rn, n with an n. Rn. The other one is Rm. Sorry, that's my italic writing. Beautiful calligraphy. Well, not here, but anyway. So actually, what we are going to do now is to show that this function is linear. So what do we need to argue to show that T is linear if it is a matrix transformation? Well, we have two properties that all linear functions must have. So what we must show is that this T, this function T, actually has these two properties. And what are those two properties? One of them has to do with addition of vectors. The other one has to do with multiplication of a vector by a real number. Okay, so property number one. What we want to check is that T of x plus y is equal to T of x plus T of y. Well, let's see whether that's the case. Now, T is induced by the matrix A. So this means that T of x plus y is equal A times the vector x plus y. But what is this equal to? Now, if these were numbers, how would you simplify this expression? And in fact, the property that you're going to use to simplify this expression also works for matrices. Absolutely. One of your colleagues is saying it's A times x plus A times y. You distribute. Any doubts about this? No. But what is A times x? Well, that's T of x. What is A times y? It's T of y. That's what we wanted to show. This is exactly this. So let's make it red. That's the way we go from here to there by going through these equalities. So far, so good. So if you have a matrix transformation, it satisfies one of the properties that linear functions must satisfy. Well, how about the other one? So what is the other one? Property number two. We want to argue that T applied to A times a vector x is equal to A times T of x. And this should be true no matter what A and x are. But hey, you know what I'm about to do? Press the extend the page twice. So what is this? Well, that's the matrix A multiplied by the vector A times x. And now one of the basic properties of matrix multiplication tells us that is A times AX. But what is this? It's exactly what we wanted here, because this thing here is T of x. So, bingo, in case you like that game. And if you don't, end of proof, smiley. we've shown that any matrix transformation satisfies both properties that linear functions must have. So every matrix transformation is linear. In fact, this is a proof that you could have done at home at your leisure at any time in a jiffy over a cup of your favorite beverage, whatever that may be. Normally, I would say a glass of wine, but I mean, here I'm probably not supposed to say that. Ach, I said it. Anyway. Okay, so far so good, but it's only half of the story. Is it possible that there are linear functions out there that are not matrix transformations? Or is every linear function induced by some matrix? And you know what? The cool thing is that the answer is yes. Every time somebody gives you a linear function, you can find a matrix that induces it. So every linear transformation is a matrix transformation. And you can actually figure out what the matrix is in n easy steps, where n is the size of the dimension of the power of n, of r, that you choose to start with. Shall we do it? Well, yeah, let's do that. People here are saying, yes, we want to see it. And because they know that even if they didn't want to see it, we have to see it, so let's do it. So bite the bullet, but you will see it's easy once someone shows it to you. That's how I felt when someone showed it to me. I thought it was magic. And I think it is a little bit of magic, but like most things that look like magic, there is no magic. It's just thinking, which is what you can do better than anyone else, because you're computer scientists. We are thinking machines. Well, you are thinking machines. I just watch you think. Okay, so let's do it. That's an N. That's an M. Okay, so this thing is linear. What I want to show you is that you can always find a matrix A such that T of x is equal to A times x for every x in Rn. Always. And in fact, there is a standard recipe that works. It's like when you bake waffles. Standard recipe, it always works if you bake waffles. So how do we do that? Let's consider first an example, now, because real teachers do examples, not the general theorems. And let's consider a function t, say from R2 to R2. And this function should be linear. So let me pick this function here. People here are really excited. Even you at home can sense the excitement. So I just took a random function. It doesn't really matter. It just sums the two coordinates, and then it takes the first coordinate as the second one of the result. Okay, so let's see. How can I find a matrix that induces this function? Well, you know, I told you before that a linear function, the behavior of a linear function, is completely determined by what it does on a small number of vectors. In this case, since this is a function from R2 to R2, all we need to know is what t does to two vectors. And you know what these vectors are? The two columns of the identity matrix of size 2. So we ask ourselves, what is t of 1, 0? Well, we don't need to guess, we just need to calculate. So what is it? It's 1, 1. Because 1 plus 0 is 0, and then we take 1 as the second coordinate. What is t of 0, 1? Well, 0 plus 1 is 1, and then we put a 0 here. So, what do we do with these two vectors? Well, we use them as the two columns of our matrix A. Does this A induce the function t? Let's see. All we need to do is to multiply this matrix, sorry, that should be a 0, by a vector xy. And let's see what happens. Well, 1, 1 times xy, that's 1 times x plus 1 times y. Hey, that's x plus y. 1 times x plus 0 times y, that's x. Oh my golly. That's exactly what t does. Magic. Well, not magic. That's the way it is. It always works if t is linear. Always. So let me give you an exercise. Suppose I now give you a function, and just for the sake of variety, let's call it f instead of t, so that you don't get overly confused. And let's say that that f goes from R3 to R2. And let's say that f of x, y, z is defined as x plus z, 0, y. There's nothing holy about what I did. I just wrote something that crossed my mind. So what is the matrix that induces F? Okay, so first of all, oh, sorry, what am I doing here? First of all, you should have reminded me that I said R2 here. So let's remove this. The result should be a vector of size of dimension 2. So, ladies and gentlemen, what is the matrix? First of all, what should the dimension of the matrix be? Okay, so this goes from R3 to R2, so it should be 2 times 3. 2 rows and 3 columns. Why? Because it should be, so our A should be such that you feed it with a vector x, y, z. So it should have 3 columns, otherwise it's not possible to do this multiplication. And the result should be something with 2 rows So A must have 2 rows. So A has dimension 2 times 3. You always you look at the size of the codomain, that will be sort of at the dimension of the codomain. This will tell you how many rows you have. And you look at this will tell you how many columns you have in the matrix. So what is this matrix? What is this matrix? Okay, so what we need to do is to ask ourselves, what does F does to each one of the columns of the identity matrix of size 3? And this will be the 3 columns of the matrix A we are looking for. So what are they? What is F of 110? 1 plus 0, 0, so it will be 1, 0. So I write a 1, 0 here. What is F of 0, 1, 0? 0 everywhere. What is F of this thing? 0, 0, 1? 1, 0. Does this work? Well, let's multiply it by X. Let's multiply this by X, Y, Z. And let's see what we get. Okay, X times 1 plus 0 times Y plus 1 times Z, X plus Z. And if we have a linear combination with all 0 times something plus 0 times something plus 0 times something else, we get 0 out. You did it. Fantastic. Thank you very much. But so what's the recipe? Well, the recipe is as follows. You look at your linear function. Goes from, in the general case, from Rn to Rm. You want to figure out what matrix induces this linear transformation? Easy, elementary, Dr. Watson. What do? You build a matrix of dimension m times n. Note, this gives you the rows. This gives you the number of columns. You just swap them around. The size of the codomain becomes the number of rows. The size of the domain becomes the number of columns. So far, so good. Now you want to figure out what are the entries of this matrix. And you do that column by column. And how do you do that? You ask to T, what do you give me if I feed you with all of the columns of the identity matrix of size n? So the first column will be T of 1, 1, 1, 0, 1, 0, 0, 0. The second will be T of 0, 1, 0, 0, 0, 0, 0, and so on. That's the matrix. Is it difficult? Sort of. Perhaps not. But that's how you do it. So what is the message? The message is that being a matrix transformation, being induced by a matrix, the fact that T of X is some matrix A multiplied by X is exactly the same thing, even though it doesn't look like it on the face of it, of T being linear, of satisfying these two properties that we mentioned before. So if somebody asks you, well, Tina convinced me that, if you're, probably there are no Tinas in here, but anyway, it doesn't really matter. It's a name that crossed my mind right now. Tina convinced me that this function t that I have is linear. Well, you can either show that it has the two properties the linear function should have, or you can exhibit a matrix that satisfies it. You want to show that that's not linear, well, you either show that it breaks some of the properties the linear functions have, or you show that there is no matrix that can induce that transformation. In fact, very, very, very often, what you can see is sort of is a telltale sign that something is wrong. For instance, suppose I now ask you, well, instead of Tina, let me say Sigurd Bjartur. Any Sigurd Bjarturs in the audience? Perhaps not. Okay, suppose I give you a function that looks like this. And I ask you, is T a matrix transformation? What would your answer be? The answer would be no. What would be the easiest way to convince somebody like me who doesn't believe in anything? Absolutely. Your colleagues here are saying, well, a matrix transformation always maps the zero vector to the zero vector. This one, if I feed it with the zero vector, it will return the vector 2, 0. Two, 0. So, not linear. Garlic necklaces, that's bad. We don't like it. Here's another example. Suppose somebody asks you, well, is this function here linear? Sort of a matrix transformation. T of xy is equal to x times y. Is this linear? Or is it a matrix transformation? It maps the zero vector to 0, so that doesn't tell us anything, but
it's not linear because if you have 2x and 2y, you get like 2 squared.
okay. So let's see. Okay, so your colleague is saying, let's see what T does to say to the vector 2, 2. The result is 4, because it's 2 times 2. Now, if T were linear, that should be the same as T of 2, 1, 1, which is 2 times T of 1, 1. But what is T of 1, 1? It's 1, because 1 times 1 is 1. 2 times 1 is 2. Ouch, that's not 4. So, not linear. Now, think about it. When we were defining linear combinations, we had always expressions of the form A times x1 plus B times x2 plus, where A, B, and whatever else, the multiplying coefficients are constants. You never had the term like x1 times x2 times x3. That's already should have spelled some danger. Okay? On the other hand, if I ask you, is this transformation f from R2 to R2 is this linear? I'm just making them up on the spot, basically. But so what would your answer be? Can you come up with a matrix that induces this transformation? It would be a square one, absolutely. Your colleague is saying it would be a 2 by 2 matrix whose first column would be what? So it would have to be T of 1, 0, which is 2, 1, 1, 1, 1. 1 and 1 minus 0, that's 1, 1. And T of 0, 1 would be the other column, which is 0 minus 1. Sorry? Yeah, so it's 0 minus 1 because x is 0 and 1 and y is 1. So 0, 0 minus 1 is minus 1. Anyway, you can check it. You just multiply this by xy. And on the first thing, you get x, and then you get x minus y. That's exactly why this works. That's exactly this. So this transformation is induced by a matrix, which means it is linear. And now, before people start firing shots at me, darts at me, because it's 13:55, let's close the session right on time. Any questions while we close the session right on time? Just to be a little bit late? No, just to answer questions.
So you can't do linear with squares.
But the question is, you can induce linear transformations with square matrices? Sure. You can induce linear transformation with any matrix, no matter what the size. Because linear, well, infinite dimensional matrices, that's a different ballgame. And there are infinite dimensional vector spaces, but you will never see them in this course, or even in the linear algebra course. Thank you very much. You know what? It won't allow me to stop. This is Gremlins today.